Alright, last video in the series. So now we are ready to solve the Garman Kohlhagen PDE. So the first we've come, just to give a little summary, I've come from the first video deriving the PDE to the second video. I showed some change of measure results. Those were important. So through those, those changing measures, we got two SDEs. One was under the measure QD, and the other one was under the measure QF. So importantly, in the third video, we then solved those SDEs, and so this is where we ended up. And so now we have all the tools that we need to solve this equation. So let me write, just so we have it here. So we have the two important solutions. We have the two important solutions. We also had, from the very first video, I'll write it here, the PDE. Now here, if you recall, I'm using subscripts to denote partial derivatives. RF. And of course with the terminal condition that at maturity it's equal to our payoff function. Alright, so let me get all that in then. Okay. So these are our main equations that are going to now bring us to a solution. So again, I prefer to do these via Feynman calc. So I will lay out that framework a little bit here first. What I'm going to do is, in case you want to go yourself and do a little research on it, I'll give the framework in the same notation that they use in Wikipedia. And then what I'll do is I'll then show you how we're going to substitute and make analogies to our particular problem. But just to lay the groundwork, and if you want to then go do research yourself, maybe this will help. You'll be able to just carry over the same notation. So basically what Feynman calc, and I also have a video on this for the Black-Scholes series. It's the same idea in deriving that solution. So Feynman calc tells us that if we have and these, I think I mentioned this in the first video, this is why I like to use subscripts, because I'm very sloppy with my partial derivative notation. That's, I guess, better. So Garman Kohlhagen tells us when we have a parabolic PDE of the following form. Plus 1/2 sigma squared x t and also with some terminal condition. So when we have a parabolic PDE of the form, this form, with some terminal, this is a psi, by the way. Let me redo it, it's awfully sloppy. Some psi function of x. The solution can be written as a conditional expectation. Q those are taus, by the way. And this is multiplied by this term. Times that psi function of the terminal given that x at t equals some little x. So under a measure q, and such that x is an Ito process driven by the equation all right, so we see great applicability to what we've done so far. So first things first, for us, we don't have this function f, so we're not going to have this term. Likewise for us, I'll say for us, the little function f is equal to 0. For us, v, this function v here is, of course, for us, the interest rate. I'll say rd. Also psi, this really doesn't matter at all, but just to be clear, I was using phi, capital Phi. Okay, and also somewhat importantly, this is constant, and therefore we don't need that integral. I'll write it like that. What else? So we have our Q process. For us, you know, we have a QD, just given the model that we're using. That was just for notational purposes. And let's see what else we can say. Right, so we have, obviously we have this Ito process under QD. We also have one under QF. That'll come in a little bit later. But for now, it looks like we are, yeah, we're doing very good. Oh, and also for us, so hopefully not too confusing for us, I said V, the way Wikipedia is using it, is equal to R. But for us, we're going to say then U is equal to, so here, we called it both big F and also pi. So it's just the pricing function. So let's, I know that might have been a little confusing, hopefully not, because this is an awesome concept, very, very useful. But let me clean this up a little bit. So for us, what we're going to say is that pi, our pricing function, is equal to the Q expectation. Again, we saw that term falls off because we didn't have any F, is equal to, again, we have a constant R. So we're just going to have an easy negative R d. I guess maybe I misspoke a little bit earlier. It's not that we don't have it's not that you forget about the integral, it's just that we don't have this sort of dependent function, it's just a constant, so it's just a super easy evaluation of the integral. You're just going to get negative RD t minus t. So, sorry about that. It's not that we don't have the integral, it's that we get to simply write it like this right away, just because we don't have this any kind of, you know, dependence there. The rate's just constant through time. So we have, okay, negative RD t minus t, okay, and then times for us, we write the payoff function as psi, or sorry, phi rather than psi. And for me, instead of writing this little, you know, given that this notation for, so this vertical line, given that xt equals some little x, I'm going to instead write it like this. I'm going to subscript the expectation. Okay, so as you can see for us, it just got far, far simpler. And then for us also, remember, then we had dxt was equal to rd minus rf xt plus sigma xt dwq of t. So, likening it to this equation up here, we have that this part is equal to the mu of xt, and this right here is equal to that sigma xt. Okay, so let's move forward now. So for us, first thing to note is that our payoff function, we had, so we're going to do this for a European call on just a pure currency option. So the payoff function is, you know, just like it would be for, say, a stock, minus k or 0. So if we fill this into our function here, we can thus say that pi is equal to the q expectation, given that xt equals x, of t minus t, and then I'm just going to fill that in like I said, max or 0. Okay, let's take this and split it up under the idea that, you know, this is basically greater than 0 when xt is greater than k. So, and then we can use that idea along with indicator functions to split it up like this. So it would be, so the first part, when I say split it up, I mean basically linearize these two terms, times xt. So this is how I write indicator functions. So I think some people write them as like thick solid ones, or like super bold I's. I like to use the, what is it, a chi, I think is the Greek letter. So this, what I'm saying is, that's how I write indicator functions. So indicator function, again, this one is that x at terminal is greater than the strike. And then we then also have minus, so now we're doing this part. Minus the same idea. T minus t, and then this time k clear, times the indicator function. Again, same thing though, that xt is greater than k. All right, so finally, no, we'll leave it there for now, and we'll call this 1 and we'll call this 2. So let's do 2 first, because it's a little bit easier. So I guess the first thing to, let's see here, yes, okay. Yeah, we'll do 2 first, because it's easier. So given that this isn't conditional, again, because we have a constant rate, and also k isn't conditional, it's just a constant. We can write this as, write this as negative k e negative r d t minus t times the q expectation, given that x at t equals x, and just times the indicator function that x at t is greater than k. Okay, but now that we were able to move these terms out, what is this then? Well, the expectation of an indicator function is simply the probability. Oh, by the way, we are not, for us, there really is no q given the way we're doing our notation. There's qd, sorry about that. So it's just the probability, so the qd probability that the event occurs. So the qd probability that xt is greater than k. But, okay, well let's work this term. What is xt under qd? Now you're going to see the importance of figuring out the solution of those SDEs. We figured out last video that under qd, the solution to xt was rd minus rf minus 1/2 sigma squared. Wait, that's... Sorry about that. It was the initial condition, or the initial value, sorry, times exponential of rd minus rf minus 1/2 sigma squared t minus t plus sigma w qd, and then I denoted it like that with a subscript. Alright, so that is what we would fill into this. That's xt under qd. So we would have that 2 is equal to negative k e negative rd t minus t times the q probability that again, that's greater than our strike price. So let's start to work this. So first thing I would do is I would divide both sides by x, and then I would take logs to get rid of the exponent. So in doing that, I would have negative k e negative r d t minus t times the QD probability that RD minus RF minus 1/2 sigma squared T minus T plus sigma D is greater than, so at that point it would be ln of K over X. Alright, so then I would subtract this term from both sides, leading to negative K to the negative domestic rate times QD probability that sigma WQD is greater than ln of K over X minus RD minus RF minus 1/2. Sorry. Wow. Okay. So what I'm going to do is I'm going to now normalize, because I'd like to get this as a standard normal variable. So realize that this is approximately normally distributed with mean 0 and variance sigma squared T minus T. So I'm going to standardize it by, of course, doing X minus the mean over sigma. So that means that, standard deviation, then this number is simply sigma root T minus T. So what did I have to do here to standardize it? I had to subtract the mean, which is 0, and then divide by this. So obviously I need to do that to both sides. So in standardizing this variable and likewise doing the same operations on this side, I will be led to negative K negative RD times QD probability. And I'm going to call my new standard normal random variable simply some gamma greater than, and then again I'll have having to do those operations on the other side. I'm not going to subtract 0, simply going to divide by, again, that. Alright, and now I prefer to get this less than so I'll have gamma is less than, and then it'll just become ln of X over K plus G minus RF minus 1/2 sigma squared T minus T over sigma root T minus T. And why was that important to get it in gamma? Some standard normal variable is less than some number. Well, this then is just the cumulative distribution function. Standard normal cumulative distribution function. It's often, simply denoted in option pricing framework as N, and then this usually then gets the moniker D2. I'm going to call it D2X. Actually, not that. I'm gonna superscript it just to differentiate it from D2 of the Black-Scholes model, which is of course just R here, because we don't have the two different interest rates. So But that's a good kind of check to see kind of the analogous logic here, is that this is just like D2 of the Black-Scholes model, except there you only had a single interest rate. So anyways, the point is you can rewrite, so this little thing is D2, and then this whole thing then would be, again, the standard normal cumulative distribution function, or n. So it means this whole thing then is simply n of D2, which means finally 2 is simply equal to negative k e to the negative rd t minus t times n of that d2, which we define by this. I really don't know why that happens sometimes. It's very, very, very strange. Okay. All right. So that's good. That's half the battle. Now we need to move on to 1. Let me turn on a light here. So what makes 1 a little tricky, you'll see it, if we recall, 1 was that and it was x times the indicator that x t is greater than k. So 2 is easy because we had a k here, right? We had an unconditional variable. It's just a constant. However, this one, it is conditional. We can't just pull that out. So basically what this is saying is it's the expectation of xt given that it's greater than the strike. So we have a conditionality that doesn't allow us to just pull it out here. Make this a little clearer that it's a chi again, not a lambda. So what can we do? Well, I guess realize that this is actually, so I should say we could take this, assume that this was the only part of the pricing function. So, or you don't have to do that, just say that this was pi 1. So our full pi then would be equal to pi 1 plus pi 2, and so then this would be pi 2. Okay. So realize that there is actually an implicit denominator here of the domestic bond at time little t, but since time little t is right now, that would just be equal to 1. So, and then this could also be thought of as a denominator. What I mean by that is we could think of this instead as not pi t. Pi 1 over the domestic bond at initial is equal to the QD expectation that we would just have t and then it would be over, and then it would be at big T. So that's rewriting this instead as that. So why write it like that? Well, it'll make a lot more sense when we change measure. So we're going to change the numeraire here, because I'd really like to get rid of this conditionality term, or I should say this conditional term. Get rid of the conditionality there. So I'd love to be able to cancel out this x. So we're going to change measure from the change numeraire from the domestic bond to the foreign bond in domestic currency. And if you remember, that is simply equal to the exchange rate times the domestic bond. Sorry, the exchange rate times the foreign bond itself. Sorry. So in doing that, we'll rewrite. We got to make sure that we're doing it on both sides. So we will have that pi over the initial foreign account in domestic. And now we change measure to, this is our change to QF. So this is a change in numeraire, but the change in measure is from QD to QF. So we have to change our expectation to QF, and it's going to be xt times the indicator that xt is greater than k over this new numeraire BF. These are both, let me rewrite that to be clear. They're both going to be as of time big T. So, importantly, we see that we are now able to cancel then that xt. And sorry, this is not the tilde process. It's just the raw BF. Okay, so let's rewrite this. And first thing, let's remember a couple things. That the foreign bank account in foreign currency at time big T could simply be written as, given that it's in a, I'll say 1 over e to negative rf t minus t, just like we had been writing, you know, the domestic account there. And also that the foreign account, the initial value of the foreign account in domestic currency is simply the exchange rate, right? So it's x at time t. Why? Well, again, think of it like the little t's are basically zeros. It's right now. And if I have a foreign account in domestic currency, we're considering that the initial value of the domestic account is 1. So if I take, you know, immediately at time little t or time 0, if I take 1 unit of the domestic currency and put it in the foreign bank account, assuming no frictions, it's simply the exchange rate. So in the end, we'll have that pi 1 over x t is equal to the QF expectation, that e to the negative rf t minus t times the indicator. That's an indicator that make that a little clearer by taking a little piece off there. Okay, now I'm going to move this out because it's not conditional, because RF is a constant, and I'm also going to move this over. So we'll have that the first part of the pricing function is equal to the initial value discounted at the foreign rate times the QF expectation, that the underlying exceeds the strike. Great, now we have something a lot easier to work with, because again, we just have an expectation of an indicator function, right? So it's just the probability again of the event occurring. So we have negative RF t minus t times the QF probability. That's simply the terminal underlying at terminal time is greater than the strike. Great. Now again, we see the importance of already having xt under QF figured out. If you recall, that was equal to the initial times exponential of Rd minus Rf, and now under QF it changed from minus 1/2 sigma squared to plus 1/2 sigma squared, t minus t plus sigma WQF, and then I just used a subscript t minus t. Alright, so same idea. Let's fill that in. So that means that pi 1 is equal to the initial discounted at the foreign rate times the QF probability. And these are just to keep the notation clear. When I say QF probability, it's just probability, how the normal concept. It's just to really denote that xt is under the measure QF. So it's the probability given that xt is under the measure QF. But you don't have to think like, well, what the hell is a QF probability? No, it's just probability, and that's just denoting that xt, though, is under the measure QF. So it's the QF probability that the initial times, so I'm just now filling in this equation. Minus t plus, and if you followed along well, or know the same idea with black shoals, you're probably, you can already see how this is going to lead to the answer. Okay, so again, I will divide both sides by x and also take logs to get rid of that. So when doing that, we'll have that okay. Again, then I'll subtract this from both sides. Sigma WQ. Okay, so again, I'm going to normalize this. So that's again normally distributed with mean 0 and variance sigma squared t minus t. So in normalizing it the same way we did before, and making sure to do, so we're going to end up subtracting 0 and dividing by sigma root t minus t. So doing that to both sides and also calling that new all right, the note sheet must have gotten really bogged down because it was just, it stopped cooperating. I hadn't changed it for the entire problem, so sorry about that. But anyways, we're at the point where we're at the point where we figured out that pi 1 should be equal to the initial value discounted at the foreign rate times the QF expectation that sigma WQF is greater than So we were at this part, and then I started to talk about, again, we want to normalize this variable. It's approximately normally distributed with mean 0, variance sigma squared, t minus t. And so again, same idea, we're going to normalize it by subtracting that mean and dividing by sigma. So basically what we're going to do is subtract that mean of 0 and divide by sigma root t minus t as before. And we just have to make sure then to do that operation on both sides. So we will get that pi 1 is equal to again discounted initial value times EQ, and I'm going to call it again just some standard normal random variable gamma. So then we have that that's greater than k over x minus r d minus rf plus 1/2 sigma squared t minus t. I'm not going to subtract the 0, I'm just going to divide by root t, sigma root t minus t. Okay. Again, let's get that to be less than, so that's going to be ln of x over k, and then plus r d minus rf plus 1/2 sigma squared t minus t divided by sigma root t minus t. All right, so again, this we'll call d1 superscript x. So again, you see the parallels with the Black-Scholes. We now have plus 1/2 sigma squared, just like d1 and Black-Scholes. It's just this time we're with an exchange rate, so we have the two interest rates here. Other than that, this is just like, and of course, you know, x here instead of s, but just like d1 of the Black-Scholes. And you could see that's why in Black-Scholes you get, there is that difference between d1 and d2. It's because d1, we have to change measure to qs to get rid of that conditional term and be able to work through it. And changing to qs, we get that plus 1/2 sigma squared. So analogous idea. And then this whole thing again is just a standard normal cumulative distribution function. So we're going to have that this whole thing is equal to n of d1. So again, we had that, we said that the full pricing function pi was equal to the one that we have done for the first part plus the second part. Split those off into two components. We just figured out that the first part is equal to the initial discounted at the foreign rate times n of d1. And we figured out that pi 2 was equal to negative strike discounted at the domestic rate. Sorry about that. Times n of d2. So bringing it all together, we have, I'll call it pi of x is equal to the initial discounted at the foreign minus t d1 of x minus k discounted at the domestic n of d2. So another way to look at this, and I hadn't mentioned this before, probably should have, And maybe I'll do a video on this stuff too, but that's the solution. So that's the pricing function for a pure currency option, and it ends up being just like if we had a stock with a continuous dividend yield Q. So again, I might do a video on that, but if you look, this is just like the solution to a stock with an underlying continuous yield of Q, and in that case, RF would just be replaced by Q. And effectively everything, like you'd have the dynamics. So for instance would be, you know, things like R minus Q, blah, 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 instead of RD minus RF. So I don't know why it's important to bring that up now, but anyways, so if you know the solution to a, you know, Black-Scholes with a dividend yield, that this pricing formula should look familiar to you, because it's just the same thing, except the dividend yield Q has been replaced by the foreign risk-free rate. All right, so that is it. That is how you derive the solution to the Garman Kohlhagen PDE using the Feynman formula. So that concludes our 4-part series in dealing with that model. Yeah, I'll be back with more videos at some point. Again, I think next I'll do the Black-Scholes with dividend yield, but I might just make that one video. I don't want to do this whole 4-part thing because, again, I think I'll just refer people to this video and the Black-Scholes before, and say draw analogies and just kind of show results. Just sort of present the dynamics and the solutions and dump those into Feynman and you know, refer them to these if they need to sort of confirm what's going on. And I think I'll also do some videos about deriving the solutions for exotic options via Feynman maybe some more things with gears and off and likelihood processes, but we'll see.